Hi everyone. Today we are gonna start a new topic. We have to jump several chapters forward, and we are gonna move on to chapter 22 in our textbook. Okay, so we are gonna start to discuss the graph algorithms. So before we talk anything about the algorithms, well, first we have to define what is a graph. So for a graph G, and the definition is it has two things: a collection of vertices and then a collection of the edges. Okay, so for the V, it represents the set of the vertices, and then for the E, it represents the set of the edges. And for the edges, given we have that many of the vertices, and the most number of the edges we can do should be the number or the length of the V squared, which means if we do have V, the number of the V squared, that many of the edges, and then we have a full graph, because if we randomly pick two nodes or two vertices and they are connected, so we have a full graph in this case. Well, and this O means, well, this is the upper bound, and of course, well, if the graph is not full, we are perfectly fine with it. And there are a few variations of the graphs, and the first one is a connected graph, and it has from every vertex to another. So if you randomly pick two vertices, and you can always find a path from one node to another, and then you can call that a connected graph. And the next one, an undirected graph, and that is the edge between U and V is the same to the edge from V to U. So, well, no, if we pick up a U and a V, and then there is only one path between U and V, and it is undirected. It doesn't matter you go from the U to V or from the V to U, and that is the same path. Okay, and another definition is, well, remember, for the undirected graph, and there's no self loops. And the other side, how about a directed graph? So for the directed graph is, well, for the edge U to V, and this goes from the vertex U to the vertex V, and note it as U to V. Okay, so if we want to draw that here, so if we have the node U, node U, and then the node V. And if you want to do a undirected graph, and then there is an edge between U and V, so it doesn't matter that we want to go from U to V or V to U, well, because that is the same edge. However, if we are talking about a directed graph, and we are doing an edge from U to V, okay, in this case, well, we can only follow this path from the U to V. However, we can't go back. So this definition is only for an edge from U to V. But is there a way to go back from V to U? We don't know about that. Okay, so the next part, the weighted graph. So just now, no matter we are talking about directed or undirected graph, we are only defining whether there is a path or a route from U to V. Well, and in the weighted graph, we can say there is a weight. So the weight is 10, for example. This can mean, well, the cost from U to V is 10, or the distance from U to V is 10. But anyhow, we can attach a weight to each of the edge. So let me go back. Okay, and then the multigram. For the multigram, well, for each pair of the nodes, there can be multiple graphs. So for example, like I have U to V and then V to S, for example. Okay, and then the weight is a 5. And from the U to V, I have another path, and this weight is 15. So in this case, from U to V, there are two possible passes, right? We can do this way, U to V, and that's the cost or the the weight is a 10, and then if we want to do this way from U to V, and then the weight is a 15. But from U to V now we have two possible paths. Okay, let me go back to my lecture notes. Okay, so typically when we are talking about the density of a graph, we are assuming or we understand that a graph won't be 100% complete. So for example, if we want to see this one, there's no direct path from U to S. We can do U to V and then V to S. U to V and V to S. However, there's no direct way, or there's no edge directly go from the U to S, right? So in this case, well, this graph is kind of full, but not that full, I would say. So how do we define how full a graph is? So typically, oops, I made a mistake again. Okay, so typically, if we find the number of the edges is roughly equals to the number of the vertices squared, and then this is a dense graph. This means even though this graph is not complete, and it is somewhat complete, or it is somewhat dense. On the other side, if the number of the edges is roughly the same number to the number of the vertices, and then we say this graph is a sparse graph. Okay, and the next part, how do we represent a graph? Well, the first thing we can do is adjacency matrix. So for example, if we have the vertices from 1, 2, 3, and then all the way to n, so we have a total of n vertices. And if we want to define a adjacency matrix, and what we can do is, how about we just create a n by n matrix, and then for each of the value with the I and j as the x index and the y index, and it is a 1 if there is indeed an edge from I to j, and otherwise it is a 0. Or if you want to use the weight of the edge, and feel free to do so. So in this case, if there is an edge between I and j instead of a 1, and then we can just put whatever weight it is. So let's just use a very small graph here as the example. So we have a total of 4 nodes, or 4 vertices, and then for the x-axis we have 1, 2, 3, 4, and for the y-axis we have 1, 2, 3, 4. And the problem is, how do we fill in this adjacency matrix? And actually, well, we have to define how do we say from node 1 to node 2. So for example, from node 1 to node 2, and they are connected. So the rule is, well, we pick the first node from a line. So that is the line 1. And then the target node is on the y-axis. So that is from the node 1 to node 2, and there is a 1 saying from node 1 to node 2, and they are connected. And if you want to do the opposite way, from node 2 to node 1, there is no such a path or an edge, so we are going to have a 0 here. So if we just follow this rule, so we pick a from, and then we pick the 2, so from 4 to a 3, and there is a 1 saying from 4 to 3, and there is an edge, and we can fill in this adjacency matrix. And for this one, we are only representing whether there is an edge or not between those two nodes. And remember, if we change this a to a 5, for example, that is the weight from 1 to 2, it is a 5. So in this case, well, this 1 will be replaced by 5. So that is also doable. So the next question is, how much does the adjacency matrix require? So that is a n by n matrix, right? And what is the n? and the n is how many vertices we have. So the adjacency matrix will take the OV square storage memory, storage memory. Okay, so the next part, what is the minimum amount of the storage needed if we just want to do a adjacency matrix representing an undirected graph? Okay, so it is an undirected graph. So for undirected graph, the edge between u and v is the same as the edge between v and u, right? So the first thing, well, undirected graph, so the matrix is symmetric. Okay, so if it is symmetric, we only need to store half of that. And another definition of the undirected graph is there's no self loop. So there's no loop between u to itself. So in this case, we don't need the diagonals. Okay, so if we come back to this example, well, for the upper well, this is a directed one, so probably that's not a good example. So let me just draw this. Give me one moment. Okay, so it is 1, 2, 3, and 4, and 1, 2, 3, and 4. So for the 1 to 1, that is 0, 2 to 2, 0, 3 to 3, 0, and 4 to 4, 0, because there's no self loops. Okay, and from the 1 to 2, there is a 1. So if we are considering this as a undirected graph, and then from 2 to 1, that is also a 1. And the same thing from 1 to 3, that is a 1, 3 to 1, it is also a 1. And then from 4 to 3, there's a 1, and 3 to 4, that is also a 1. So 1 here and 1 here. And I'm going to fill in the remaining slots with zeros. Okay, so we are still using the same example, but we are assuming that is an undirected graph. So in this case, well, the first observation is that is a symmetric matrix. So if we want to store this matrix, we only need to store either this part or this part, right? Because, well, they are symmetric, and then for the diagonal values, they are all zeros. So in this case, we only need to store a total of 6 digits. So we can either pick the upper half or the lower half, but anyhow we only need to store a total of 6 digits, or 6 binary digits in this case. Okay. Okay, so the next question, what is the minimum amount of the storage? Okay, but we have done this. Okay, so the adjacency matrix is a dense representation, and usually it is too much to store a very large graph because it is a n by n matrix. And if you are considering that if you are trying to do a by n matrix of a social network, for example, all the users on Facebook or on Twitter, and then, well, this matrix is very likely to be super sparse. There can be millions of people on a social network. However, I may only know a few hundreds of them, and that's already a lot, right? So in this case, well, the E will be the O of the V. So if I'm for the number of the edges, and that is the O of the V, which is the number of the vertices. So it is really sparse. And if you imagine that, well, there are millions of people, and for each of the people, this person only connects to, well, 200 people, and that is a big number. However, in this case, and we can say in this case, and the E, so the size of the E is 200, and then the size of the V, right? So that is already a big number. But in this case, well, this is a constant C, right? If we pick a higher number, say we pick 500, and then we can say E is always smaller than 500 V in this case. So we can say E is OV. Okay, so in this case, probably we don't really need to use a super sparse n by n matrix. And the next choice we want to talk about will be the adjacency list. And we are using the adjacency list to store a large graph, and yet we know the graph is sparse. Okay, so I'm going to continue in the next video.